Hello, and thank you for tuning in to my presentation on Seismic Fragility of a Buckle and Restrained Braced Steel Rocking Frame. My name is Alex Baker, and I'm presenting on behalf of myself and Dr. Daniel Dowden from Michigan Technological University. Before we get started, I'd like to more formally introduce myself and my co-author. I am a master's student at Michigan Tech, and Dr. Dowden is my research advisor. My research interests are in large-scale numerical studies, such as incremental dynamic analysis, and I have been assisting Dr. Dowden with his research into self-centering systems and resilient infrastructure. Introductions aside, let's get into the research. It's an unfortunate fact that, whether by design or lack of design, much of the products we use on a day-to-day basis are easier and cheaper to replace than repair. This is also true for buildings after an earthquake. Most buildings are designed only for life safety, with little regard to repairability. Because of this, studies have shown that as little as 0.5% roof or 1% inner-story residual drift can total a building. If buildings could be designed to be more repairable after an earthquake, recovery could be quicker, cost less, and be more environmentally friendly. Although there are a lot of variables that can contribute to a building being totaled, the cost of repair can be significantly reduced by incorporating structural systems that reduce residual drift, have decoupled gravity and lateral systems, and have easily replaceable yielding components. So, towards more resilient infrastructure, our research proposes a new seismic force resisting system, the NZ-BRB frame. This system is a combination of a low-damage, self-centering boundary frame with buckling restrained braces known for their substantial energy dissipation, ductility, and ease of installation and replacement. This proposed system is expected to behave similarly to a BRBF, but with the added benefits of reduced residual drift and backup elastic stiffness. So here's a drawing of the proposed system and its yielding mechanism. As you may notice, the proposed system is very similar to a traditional BRBF, but with special connection details. The two main connection details are the beam to column connection, which is the noose brace connection, and the brace connection to the beam, which is pinned and isolated on the beam. The noose brace boundary frame is utilized for its low damage behavior. The top flange rocking detail ensures that the distance between column center lines remains constant, and long slotted holes in the shear plate allow the beam to rock freely. To evaluate this proposed system, the P695 methodology was adopted as a guiding framework. This framework is an iterative procedure to quantify seismic performance factors for building systems. First, seismic performance factors are assumed for the system. Then, archetype buildings are designed using linear analysis methods. Using these designs, nonlinear models of the archetype buildings are developed and evaluated for performance. The performance evaluation then serves to validate or refute the initial assumptions. For this study, only one iteration of the P695 methodology was performed, using an R factor of 8 as a starting point. Buildings were designed based on the SAC Steel Project benchmark buildings, and design was done in accordance with applicable standards. The archetype design space that was explored was limited, only using 2 building heights with variations in PT parameters. Nonlinear models were developed in open Cs, based on previous work with noose brace frames and BRBs. Nonlinear material models were based on calibrated parameters in the literature, and failure modes such as low cycle fatigue and second-order instability were modeled directly. The nonlinear models were then subjected to the P695 far-field record set, which consists of a total of 44 ground motions, normalized as specified in the P695. The median spectra of the far-field record set was then anchored to the DBE and MCE level intensities, and the average nonlinear responses were investigated. Note that even though residual inner-story drift levels were close to the repairability limit mentioned previously, the configuration of the NZ-BRB frame should allow for easy repair, given that the boundary frame remains essentially elastic. In order to determine collapse capacity, incremental dynamic analyses were conducted on the index archetype models, and log-normal collapse fragility curves were fit to the data. The 3-story models had higher collapse capacity than the 6-story models, and in both building heights, increased levels of PT increased the collapse capacity. Similarly to the collapse fragility curves, self-centering fragility curves were developed, representing the percentage of ground motions that resulted in self-centering behavior, which was classified as having less than 0.2% residual drift for all stories. Although it did not consistently self-center, self-centering was achieved more with higher levels of PT. Unfortunately, the preliminary iteration of the P695 evaluation was not successful. the assumed R factor did not pass. It is suspected that this is due to soft story mechanisms, possibly aggravated by using the same level of PT at every floor. Additionally, as it was a preliminary investigation, the assumed quality ratings were less than ideal, which affected the performance evaluation. Since publishing the conference paper, we have developed a more rational basis for sizing the PT, widened the archetype design space, and improved the numerical modeling. The next steps include finishing the designs of the new archetype models and rerunning the IDAs to establish the preliminary seismic performance factors. Thank you for listening. If you have any questions, feel free to message me in the 17WCEE bulletin board or email me at ambaker1@mtu.edu.